Hello physics students. Today we're doing problem 3-7, which is the cart rolling down the ramp and going around the loop. Key concepts that we need for this problem are conservation of energy and gravitational acceleration. Okay, let's begin. A asks to determine the height of h. So we can use conservation of energy for this part of the problem. The potential at the end of the total ride, it takes its full loop and it goes here. We're looking at this one spot right here. The potential energy from gravitational potential, which is this, plus the kinetic energy that it gains while going around the ramp. It has speed when it goes off it, which is kinetic, is equal to the potential at the beginning, which is what we're trying to find out. We're trying to find out this height right here. Okay, so the equation for the potential at the end is 0.5 meters times m, of the mass of the cart, times gravity, which you'll just label as 10 for now, plus the kinetic energy, which is 1/2 mv squared, and m is 0.1. V is given as 4 meters per second, is equal to the height at the beginning, is equal to this height at the beginning. So height times the mass, 0.1, times gravity, 10. And just to write this out in terms, and when it's solved out, you get the height is equal to 1.3 meters. Oh. Now we'll move to part 2 of the equation, or the problem. We need to label all the forces acting on the block when it's at the center, 0.5 meters in the loop, which has a radius of 0.5. So the forces acting on the cart would be the normal force going this way, act from the section of the curved loop. So the normal force is going that way. We'll label that as N. And there is gravity acting on the block as well, which will be labeled as mg. And this is part B. And that is how you get the forces on the block and draw it up. For part C, is asking to determine the magnitude of the force exerted by the track on the block, which is another fancy way of just saying what is the radial acceleration times the mass on the block. So the equation to get the radial acceleration, F is equal to mass times acceleration. So F is equal to the radial or centrifugal acceleration times the mass of the block. So F is equal to m times v squared over r. And you can just plug in the values now. So the mass is 0.1. 0.1 times the speed, and since it's the same height, since it's at the same height, the speed at this point is the same as the speed at any point along this plane. So the speed is 4 meters per second, and that is squared over the radius, which is 0.5. And once that is solved out, you get that the magnitude of the force is 3.2 newtons. Now for part D, which will probably move to a different sheet of paper if we lose out of room. And I'll just keep you on hand. Alright. Determine the maximum height above the ground achieved by the block after it leaves the track. So, alright, this is just gravitational acceleration. You have to find the speed in the y direction of the block. And this is when the angle of 30 degrees comes at hand. It's so hard to move all this stuff. Alright. The cart leaves, or the block leaves at an angle of 30 degrees. So you need to split up the 4 meters per second into x and y. And we don't need to worry about the x. So let's just focus on the y. When it is going horizontal, the speed in the y is 0. So that tells us that we need to use the sine of theta 4 times the sine of theta to get the speed in the y. We'll label that Vy. So sine of 30 is 1/2, so 4 times 1/2 is equal to 2. So that is the speed in the y. And we'll use that to determine its maximum height. Okay, when it reaches its maximum height, that means that the velocity, at least the y velocity, is now 0. So that means that the acceleration of gravity brought the y velocity of 2 down to 0. So you can use the equation v naught minus at is equal to velocity at a certain instant. So the initial v naught is 2. So we have 2 minus gravity, which would be the acceleration, 10 times t is equal to v, is equal to 0, because it reaches the top of its point when the y velocity is 0. And we can solve this easily. So we get 2 over 10 is equal to t, or 1/5. And now we need to plug this into the equation to get how high the cart actually traveled. And I'll just move to over here for now. So the the equation for how high the cart, any object, travels, if the only forces are acting are gravity, are the initial y velocity, so v naught t plus minus 1/2 at squared. And we have our initial v naught is 2 times t minus 1/2 10t squared. And we can bring out the t that we found before, which we found to be 1/5, and we plug this into the equation. And we get that the change in height is 1/5, which seems to be very coincidental to the time. But now we have to add the initial height it started at. So we get the initial height is 0.5 meters, 0.5 plus 1/5, 1/5 of a meter, and that is equal to 0.7 meters. And that is the maximum height it makes on its curved path. Now then, we can move on to part E. My bad. I don't want to repeat that part. That was a mouthful. Another track has the same configuration, but is not frictionless. Okay, for this problem, part E, it may seem confusing, but all you have to use is the work, because all the work at the end of the track, that it loses is all due to friction. So an easy work equation can be used. So we have 2 mg where 2 is the well, 2 mg is equal to 1/2 m times the final speed 4 squared plus 0.5 times the mass times g, which is 10, and this can be labeled as 10 too, plus the work lost by friction, which I'll label as the friction, just F. And of course the friction work is always negative, so because it's slowing down, it's not adding to the the total speed. So we'll just keep that in mind. And we plug in all the values. And we get that the friction lost, or the friction work, is equal to negative 0.7. Negative 0.7 joules, I would believe. And that is how you do problem 3-7. I'll be showing the slides again with more of it showing, not like how I was recording. Problem A. Problem B, C, and D. And problem E.